So last lesson we talked about air pressure, how nature hates unequal pressures. And the only way it can equalize pressures is from taking high pressure and going to low pressure. Let's say your friend and you both have money in your pocket. Your friend has 20 bucks and you have 10 bucks. The only way you are going to have the same amount of money is if you steal 5 bucks from your friend, or your friend gives you 5 bucks. The person who has more has to give to the person who has less. It doesn't work if you give any money to your friend because you end up with less. Well, the same works with air pressure. The only way to equal the air out is to go from high to low pressure. You can take 2 cylinders like this and put more water in tank A and less water in tank B and connect them with a pipe of some kind. And if you let the water flow between the tanks, it's going to flow from the tank with more into the tank with less. And that motion through the pipe is a net force. That's called a pressure gradient force. This happens in the air all the time. The only way to equal the air out is to go from high to low pressure. So on a map, if we know where the high pressure is on the surface of the Earth, and we know where the low pressure is on the surface of the Earth, we know the wind at the surface is going to go from the high to that low pressure. That's called the pressure gradient force. So I can demonstrate that with another balloon, and we're going to go ahead and pump some air here into this balloon and inflate it. A lot easier than blowing it up. So now this air in here is under pressure. There's high pressure inside the balloon and there's low pressure outside the balloon. What's going to happen when I let go of the balloon? Where is the high pressure and where is the low pressure? Well, obviously the high pressure is inside and the low pressure is outside here in this room. So when I release it, the high is going to go into the low and the balloon is going to fly away. The pressure gradient force propelled the balloon across the room. So there's a math formula that we can use to figure out how strong that pressure gradient force is going to be. We can calculate the difference in pressure between the high pressure and the low pressure and then divide it by the distance between the high and the low pressure. So you don't have to understand necessarily the math, but the idea should make sense. If you have someone with a whole lot of money standing next to somebody with very little money, if you want to equal the money out, there's a whole lot of money that's going to go from the rich person to the poor person. Well, the same thing works with air pressure. And also the distance makes a big difference. The closer they are together, the smaller that denominator is. That's going to give you a bigger PGF. Now remember, on the Earth that winds try to go straight, but they never do so successfully because the Earth is spinning. Don't forget that the Coriolis force is going to bend the wind right in the northern hemisphere and left in the south. So this arrow is going to bend to the right, going away from the high, and so we'll get motion more like this. That's clockwise motion around a high. If I know where the high pressure is in the United States, I know the local wind is going in a clockwise circle around it. The same kind of rule applies to low pressure. The wind is going to come in, it's going to bend to the right, coming in towards the low like this. And the wind's going to end up going around in a cyclonic direction. This is how I can forecast what direction the wind is going to blow on any given day in the future, if I know where the high and low pressure is going to be. So this is an example of a storm on the left in the northern hemisphere, and notice how the winds are circling in a cyclonic fashion. Hey, cyclone, cyclonic, that's not coincidental. On the right is the southern hemisphere, and notice the winds are going around that low pressure like a clock. That's how things happen in Australia and South America. But we're here in North America, so we're most commonly looking at the picture on the left. Don't be fooled by the myth about the Coriolis force. The Coriolis force is only going to work on big motions, going over big long areas, not small ones. So it's not going to matter for a car. If you're driving down the highway, you're going to be turning the wheel to adjust for any kind of Coriolis influence. And don't believe the baloney about a toilet. Come on, toilets don't go one direction in the north and the other way in the south. You can prove this to yourself. Go home and flush all the toilets where you live and see which direction they go. Pull water down the sinks and see which direction they go. Chances are the shape of the sink determines which way it turns. Now there's more to it than just PGF being a change in pressure over a distance. You also have to include a factor to account for that Coriolis of force. And that's a little bit of trigonometry. And we're not really going to deal with trigonometry in this class. That's called the Coriolis factor. Adding this means that the curving is going to get worse as you get farther from the equator. So if you look at an airplane flying along the equator, its path doesn't change at all. If you have a flight taking off from Florida or just above the Tropic of Cancer, it's going to bend less than someone taking off from the Arctic Circle, where it's going to bend more. So that Coriolis factor, who cares? We don't have to really worry about it. All you really have to understand is the closer the high and low pressures are on a map, the faster the wind will be. And we can easily figure that out with something called a surface weather map. This is an example of a surface map. And those yellow lines that you see are isobars. An isobar is a line of constant pressure. All over the United States, nerdy scientists like me have computers that are measuring the barometric pressure outside where they are. And the computer takes in all this information at least hourly, if not more. And what it can do is it can draw a line between all the constant pressures. So that little yellow line that runs through Virginia that's marked 1016, that's the line that connects all the pressures that are 1016 millibars. If you walk along that line, your barometer will never leave the number 1016. The highest number on that map is out in California. It's 1024, and there's a big H there. That's high pressure. This is a surface map taken during a blizzard in the Midwest. Now the blue lines are a little bit harder to see, but you see that big L next to all that rain in Iowa and snow in Nebraska and Kansas. And then look at all the blue lines that are close together through Minnesota, South Dakota, and North Dakota. And then up in Canada, you have the high pressure there. Where those lines are close together, it's windy. And the wind direction basically follows those lines. A surface map is very useful, telling me, a forecaster, where the wind direction is going to be and how fast it's going to be. Squeezed air tends to move faster. It's kind of like this hose. If you just stand here and hold the hose, it comes out at a constant speed. But if you would squeeze it, it's going to come out much, much faster. Squeezing the air is going to make it move faster as well. Take a look at the blizzard of '96, which happened here in Pennsylvania. This is the 8th of January 1996, when we had a big storm just parked off the coast of New Jersey. Notice the L with a 978 next to it. And then right off at the top, right around Quebec, there's a high with a 1020. That's a big change in pressure over a real tiny distance. So our lines are packed close together over Pennsylvania, and it's windy here. We've got a lot of snow and a lot of wind happening at the same time. It's a blizzard. Now, making a surface map isn't really as easy as I made it sound. Yes, they're getting pressures from all over the country, but you have to remember that the country is not flat. Remember, pressure is going to change with your height above sea level. So somebody living down in Florida who's at sea level is always going to have a higher pressure than somebody living in Denver, about a mile above sea level. So we have to come up with a way to standardize pressures and consider elevation when we're reading our barometers. So let's think of this fictitious example. Let's say I've got 3 people with barometers indicated by the yellow stars. This is a side view. We're looking at the ocean. So we have at sea level, someone walks outside and measures 1012 on their barometer. And then halfway up the mountain, somebody measures 970 on their barometer. And at the top of the mountain, somebody measures 944 on their barometer. Notice the pressure's going down as you go up the mountain, as it should. This is called a station pressure. The actual pressure at the station is the station pressure. And that would be important for people who are flying airplanes. But we have to consider, what would the pressure at each place be if that station was at sea level? If you dug a hole straight down into the ground, all the way to where sea level would be, and drop a barometer down there, what would the pressure read? and we can do some math to figure that out. To have a map that makes any sense, we need to adjust these to sea level. The formula we use is we're going to add 10 millibars per every 100 meters, or add 1 millibar every 10 meters. So when you're at sea level, you're at 0 meters in elevation. So you're not going to add anything. Your sea level pressure is your station pressure. Okay, you don't have to make an adjustment in this case. You're always going to have the pressure that's at sea level. Halfway up the hill, let's say they're 400 meters in elevation. Well, the easiest way to figure out how much we have to add is just to lop off a 0. We take off a 0, that means we're going to add 40 millibars to 970. 970 plus 40 is 1010. We'll do that one more time. At the top of the mountain, it's 960 meters. Go ahead and pause the video and see if you can figure out what the pressure should be at sea level at that station. Okay, you should be adding 96 millibars, and that means you should have a pressure of 1040. Now it's obvious. If all those stations were at sea level, the one on the right would be 1012, the one in the middle would be 1010, and the one on the left would be 1040. The one on the left is where the high pressure is. The one in the middle is where the low pressure is. This is known as the sea level pressure. Every surface map is created with isobars that are set to sea level pressure. That gives us relatively on the surface of the Earth where the high and the lows are. Knowing the highs and the lows help us understand which way the wind is going to blow today and in the future.